Welcome to Shanti-Peace for Mathematics. In this video, we are dealing with a sequence which will really help us to clear understanding of a series. And series play a significant role in the field of ordinary differential equation. A sequence are basically countably many numbers arranged in order that may or may not be explicitly certain pattern. Let us define a sequence formally. Sequence is a function from a natural number n to r, or it can be any codomain will be there, but the domain is n. So function whose domain is a set of a natural number and the range is a set of real number, it's called a sequence. And symbolically, a sequence denoted as fn from r. So it is fn is equal to, a notation is an. So what I say, it is a function whose domain is the set n of a natural number and the range is the set of real numbers r. It's called a real sequence. Here the word real stands for that range. If you consider your range is a complex number, then it's called a complex sequence. It can be also defined as another term. Since we are dealing with the real sequences, we use the term instead of real sequence, we just use a sequence. It's also, since the domain of the sequence is always n, that is a natural number, a sequence specify the value Sn or an, where n belongs to a natural number n. And the sequence is denoted by, there are various notation for the sequence, may be denoted by this notation Sn in curly bracket Sn, where n belongs to n. Sometimes is also denoted as by Sn n running from 1 to infinity, or some of them can also denoted as S1, S2 up to S3 up to so on. Sometimes is also denoted by Sn in the round bracket Sn, n running from 1 to infinity, or just Sn. So these are the various notation for a sequence is used. The value S1, S2 up to Sn, they are called the terms of the sequence. For example, the nth term is Sm and nth term is Sn. Now let us see some examples of a sequence. The first example I can say it is 1 by n. So it is a sequence of the type 1, 1 by 2, 1 by 3 up to so on. This is the first example. The second example I can say a -1 raised to n. So this is the sequence contains -1, first term is -1, second term is 1, third term is -1 and so on. I may define a sequence like this. Let's say an, where an is the nth digit of the Euler number E. We know that the Euler number E is nothing but the 2.71828. So here A1 will be 2, A2 is 7, A3 is 1, A4 is 8 and so on. So in that manner this sequence is defined. Now there is a classification of a sequence is there. So sequences are widely classified. Let us look at this classification. The first one is the bounded above sequences. So the definition of the bounded above sequences, if I want to say a sequence Sn, it's called bounded above sequence if there exists some number k which is a real number belongs to R such that Sn is less than or equal to k for every n, and k is called upper bound of the sequence. So this is the upper bound of the sequence. Second one is bounded below sequence. A sequence is said to be bounded below. A sequence Sn is said to be bounded below if there exists L belongs to R such that Sn is greater than or equal to L for every n is in n, and this L, it's called lower bound of the sequence. So third definition is the bounded sequence, or third classification is the bounded sequence. A sequence is said to be bounded if it is both bounded above and bounded below. A sequence is said to be bounded sequence if it is bounded above and bounded below. The notation K and L we have discussed are called, which we have discussed here. So that means a sequence Sn is there. If I want to say it is a bounded sequence, that means there exists K and L belongs to R such that K is less than or equal to Sn less than or equal to L. And this K between K to L is a range of this sequence Sn. And also the bound of the range is bounds of the sequence that we have. This fourth classification is strictly increasing sequence. So a sequence Sn is said to be strictly increasing if Sn is strictly less than Sn plus 1 for every n belongs to n. The fifth classification is non-decreasing, or I can say increasing sequence. Non-decreasing or increasing sequence. So both the word is used for increasing sequence. So instead of this strictly less than, we have less than or equal to. A sequence Sn is said to be increasing if Sn is less than or equal to Sn plus 1 for every n belongs to n. Sixth classification is strictly decreasing sequence. So a sequence Sn is said to be strictly decreasing if Sn is greater than Sn plus 1 for every n. The seventh classification is a decreasing sequence or non-increasing sequence. This is also known as decreasing sequence. So it says that a sequence Sn is said to be decreasing if Sn is greater than or equal to Sn plus 1 for every n. And the eighth one is the monotonic sequences. So monotonic sequences are those sequences which are either increasing sequences or a decreasing sequence. So a sequence Sn is said to be monotonic sequence if the sequence is either increasing or decreasing, and it's said to be strictly monotonic if it is either strictly increasing or strictly decreasing. So let us see some of the examples based on this. So the first problem that we will consider this sequence -1 raised to n plus 1. We have to check whether this sequence is increasing sequence or monotonic sequence or bounded sequence or not. So here we have S1, that is the first term, that will be 1, S2 is -1, S3 is 1, and so on. And we see that the sequence is neither increasing nor decreasing. So hence this sequence is not monotonic sequence. So what should write? We see that the sequence is neither increasing nor decreasing, and hence it is not monotonic. So it is not a monotonic sequence. Can we say it is a bounded sequence? Yeah, it is a bounded sequence because it is a bounded above by 1 and it is bounded below by -1. So we note that minus 1 raised to n is less than or equal to 1 for every n, and minus 1 raised to n is greater than or equal to minus 1 for every n. So hence the sequence is bounded above by 1 and bounded below by minus 1. Hence this sequence is bounded. Let's have one more example. Consider the sequence 1 upon n square n running from 2 to infinity. We have to verify whether the sequence 1 upon n square is monotonic and or is bounded. Here we have Sn is equal to 1 upon n square. So we have S2, that is 1 by 4, S3 it is 1 by 9, S4 it is 1 by 16, and so on. Also we note that Sn is 1 upon n square and Sn plus 1 will be 1 upon n plus 1 whole square. We note that this n plus 1 is always bigger than n. So if I take the reciprocal here, then this will be 1 upon n plus 1 will be less than or equal to 1 upon n. If I take the square both sides, then 1 upon n plus 1 square is less than or equal to 1 upon n square. And this is true for any n greater than or equal to 2. So we can say is Sn plus 1 is less than or equal to Sn for every n greater than or equal to 2. Therefore, we can say that sequence Sn is decreasing. Since it is a decreasing sequence, therefore the sequence is monotonic sequence. Monotonic sequences are those sequences which are either increasing or a decreasing sequence. One should note that all the terms of this sequence are positive. We note that 0 is always less than or equal to 1 upon n square for any n greater than or equal to 2. That means what we can say, the sequence is bounded below by 0. Also we note that the sequence is decreasing, and the first term of this sequence is the largest term of all the terms of the sequence, and therefore it is bounded above by 1 by 4 because the first term is 1 by 4. We also note that 1 upon n square is always less than or equal to 1 upon n by 4 for every n greater than or equal to. Therefore the sequence is bounded above by 1 by 4. Hence what we can say is the sequence is the bounded sequence. This sequence 1 upon n square is decreasing as well as it is bounded sequence. Let's have one more example. Consider the sequence n upon 1 plus n. Here is also we have to discuss whether this sequence is monotonic sequence or it is a bounded sequence or not. So here we have Sn is n upon 1 plus n. So we just note that what is S1, that is 1 upon 2. What is S2, that is 2 upon 3. What is S3, which is 3 upon 4. S4, that is 4 upon 5, and so on. Here Sn, we note that it is n upon n plus 1. What is Sn plus 1? It is n plus 1 upon n plus 2. To prove this is decreasing or increasing, to see that, we'll just subtract these two terms, that is Sn minus Sn plus 1. Will gives me n upon n plus 1 minus n plus 1 upon n plus 2. So this will leads to n into n plus 2 minus n plus 1 square upon n plus 1 into n plus 2. If I simplify the numerator, that is n square into 2n minus n square minus 2n minus 1. In the denominator we have the same term we have here. This n square will get cancelled out, 2n will get cancelled out. So the quantity left, it is minus 1 upon n plus 1 into n plus 2, and if n is positive, or I can say greater than or equal to 1, then this quantity is always less than 0 for any n belongs to n. What we can say, therefore, Sn is less than or equal to Sn plus 1 for every n. We can say this sequence Sn is an increasing sequence, and hence it is a monotonic. See, it is an increasing sequence, it is bounded below by 1 by 2, because the first term should be the smallest term, and hence it is the lower bound. Thus the sequence is bounded below by 1 by 2. We can see the sequence Sn, it is n upon n plus 1, and this quantity is always less than or equal to 1, because n is always less than or equal to n plus 1, which is always true. So n upon n plus 1 is always less than or equal to 1. So from this, what we can say is the sequence is bounded above by 1. So hence the sequence is bounded. So here the sequence is bounded above by 1, and therefore the sequence is bounded. It is not always possible to determine whether the sequence is monotonic in nature of a sequence considered just by investigating first few steps of the sequence. In such case, you may require to use a derivative test to determine the monotonic nature. And once we have a sequence, it is important property of the sequence whether the sequence is a convergent sequence or a divergent sequence. Convergence means it is approaching to some value. So if the sequence of the term is approaching to a finite value as a number of terms increasing, then the sequence is said to be a convergent sequence. In order to clear the understanding of convergent sequence, we need to first understood what you mean by limit of a sequence. For example, if I have a sequence Sn is equal to 1 by n for n greater than or equal to 1, if I have this sequence, then we know that the graph of this sequence is like this. That means at 0, at 1 it has a value 1, at 2 it will have a value 1 by 2, at 3 it will have a value 1 by 3, at 4 it will have a value 1 by 4, and so on. If I increasing the value of n, this is n and this is 1 by n. So if I increase the value of n, we can see that it is approaching to 0. I can say the limit of this sequence Sn with the limit of 1 upon n will be 0 as n tends to infinity. Just like a definition of a limit that we have. So here I can define a limit, a real number L is said to be limit of sequence, or I can say limit point of a sequence Sn if limit of Sn is equal to L as n tends to infinity. In the epsilon definition that we can write down for given epsilon greater than 0, there exists n0 belongs to n. So Sn minus L is less than epsilon for every n greater than or equal to n0. The meaning of this one is you have on a real line you will have this 1, 2, 3 and so on. So after n0, the distance between Sn and L you can make as much as small you can. The convergence sequence definition is said now using this limit definition. The definition of the convergence sequence is a sequence Sn to be convergent to a real number if L is the limit point of the sequence. Means if limit of Sn is equal to L as n tends to infinity for some finite number L. The idea of the saying convergence means we pass along the sequence a term get closer and closer to L. If we can say the limit of Sn is L as n tends to infinity does not exist or it is infinite, we may say that the sequence is divergent. The limit of Sn is equal to L as n tends to infinity does not exist or is defined or infinite, and we say that sequence Sn is divergent. If limit of Sn is equal to infinity as n tends to infinity, then we say that the sequence Sn is diverged to infinity. Limit of Sn is equal to minus infinity as n tends to infinity, then Sn is said to be diverged to minus infinity. The sequence is neither convergent nor diverged to infinity or minus infinity, then the sequence is said to be oscillating sequences. A sequence either diverges or is diverged to infinity or minus infinity, then sequence said to be oscillating. For example, minus 1 raised to n. This sequence minus 1 raised to n is neither converged nor diverged. So this is an oscillating sequence. Let's see some examples. We are discussing some results, but all the results we are assuming without proof. So the first theorem that, or we are saying that every convergence sequence is bounded. If you have a sequence which is convergent, it is automatically bounded sequence. Converse of this result is not true. That means I cannot say that every bounded sequence is convergent. The example is minus 1 raised to n. This is bounded sequence bounded by minus 1 and 1, but it is not convergent sequence. We know that it is oscillating sequence. So the converse of this result is not true. The second statement that we are saying, it is a sequence not converge more than one limit. I can say that the sequence limit of a sequence is always unique. It cannot be converged to more than one point. There are some results that we need to know for this sequences, that is called algebraic operation on a sequences. If you have an and bn, two sequences, both of them are convergent sequence. That means the limit of an is equal to a as n tends to infinity, and limit of bn is equal to b as n tends to infinity. Then we can have this result, that is the limit of an plus 1 plus bn, an plus bn is equal to a plus b. If it is minus, here it is also minus as n tends to infinity. So it says that a sum of two convergent sequence is convergent. Next, the product, that is a limit of an into bn is a into b as n tends to infinity. It also says that the product of two convergent sequences is convergent. The third statement, we can say that the limit of an upon bn is equal to a upon b if provided this b is not equal to 0. So we'll take this as a result. The another one is a sandwich theorem. This is also very important result known as a sandwich theorem. If you have a sequence an, sequence bn and sequence cn, are three sequences is given to us such that they are satisfying this an is less than or equal to bn is less than or equal to cn for every n, it will satisfy. If the limit of an and the limit of cn is L, limit of Bn is also L. You can say and a limit of An as n tends to infinity is equal to limit of n is equal to L, and limit of n tends to infinity Bn is also L. That means if you have these two sequences are convergent, so in between them whatever the sequence is there which is also convergent. Other important results that I need for further discussion into this, that is a limit of n tends to infinity a power n is 0 for all a between 0 and 1. So this is the first results I need. The second one, a limit of n tends to infinity a power 1 upon n is 1 for any a greater than 0. Next important definition that we required is a Cosy sequence. Many times it is not possible to find the actual limit of the sequence to determine the convergence and the necessity of criteria. With the sequence can be tested convergence using the known terms. A given sequence without having rarely unknown limits. So the concept of Cosy sequence or Cosy criteria help to get through. So a sequence called Cosy sequence, each epsilon greater than 0, there exists n0 belongs to n such that Sn minus Sm is less than epsilon for every nm greater than or equal to n0. That means that after n0, after some term, the difference between Sn and Sm is small as much as you can. And there is one result based on this Cosy sequence. It says that if a sequence Sn is a convergent, then Sn is a Cosy sequence. In fact, this result is true for real numbers, that a sequence is convergent if and only if sequence is a Cosy sequence. And also where is the one result is there that every Cosy sequence is a bounded sequence. So these are some elementary results that we need to discuss the series, infinite series. That is the aim of this chapter, unit 2 for calculus. So we'll discuss this series in the detail in my next video. These are the some, in this video I just talked about the some review on sequences, and I have discussed some examples based on that. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.